Well, very good. I'm really excited to introduce our next keynote speaker. And as I was telling him backstage, I said this is one of the few speakers that I've had the pleasure to introduce that comes preloaded with questions, and we've already got questions for Nick based upon some of the participation in the panel yesterday afternoon. So Nick Harris is the CEO and the co-founder of Lightmatter, where his team is leading the evolution of computing and reducing its impact on our planet and enabling the next great leap in human progress through silicon photonics. Prior to founding Lightmatter, Nick was an intelligence community postdoctoral fellow and a National Science Foundation fellow at MIT, where he received his PhD in electrical engineering and computer science. Nick has authored 67 academic articles and has 13 patents, and his doctoral thesis was titled Programmable Nanophotonics for Quantum Information Processing and Artificial Intelligence. Nick was previously an R&D engineer working on DRAM and NAND circuits and device physics at Micron Technologies. So really looking forward to this presentation. Reminders to folks, if you have questions, both the Slack channel is open for questions as well as the chat here in Zoom. All right, Nick, please.
All right, thanks for the intro, Alan. Let me go ahead and share the slides here. Okay. Everything good on the slides?
Yep.
All right, so really excited to be here at Hot Interconnects. I think that Interconnect really is the challenge of the day at this moment in computing history. I'm excited to tell you guys how we see things at Lightmatter and tell you about what we're building, and excited to answer the questions that are apparently piling up. So let's see here. First, we'll go into a quick agenda. We'll talk about this moment in computing history, what we're seeing, obviously the effect of AI on the network. Then we'll talk about how silicon photonics is going to be driving progress in networking. We'll dive into CPO implemented with silicon photonics and some of the challenges that go into taking that kind of technology to market. And then we'll talk about some new ideas and things that we're working on here at Lightmatter. So before we jump in, a brief word about the company. So we're about 125 people strong. We have an incredible team, people who led Google TPU, incredible chips like Ponte Vecchio and more. We have offices in Boston and Mountain View. We've raised about $300 million from top VCs. And you can bet we invent a lot of really impressive tech. And the aim for us is really about driving compute forward. So I think one of the interesting things about the company, and that gives us sort of a unique advantage, is that we look at not just the networking piece of things. We're not just a pure physical layer photonics company, but we look at the problem of computing holistically. We have experts that work on supercomputing networking, people who work on ASIC design. Name your field, we have representation. And this allows us to see the whole interconnect space, I think, a bit more holistically. And a lot of the people here have worked on some of the biggest AI supercomputers that are on the planet today. So really proud of the team and excited to share what we're up to. So let's start by talking about this, I think, very unique moment in computing history. I think at this time, Interconnect is being absolutely transformed. So we'll talk a bit about the drivers. Obviously, AI and generative models are one of the biggest drivers of what's happening right now in the AI computing space. The amount of investment that's gone into this area through venture capital and also just large companies investing in getting access to the technology and building products around it, truly, truly massive. Today, we're seeing that there are workloads spanning 10,000 accelerators running regularly. So these are training next generation generative models, large language models. And you're seeing startups raise, hundreds and hundreds of millions of dollars just to place an order with NVIDIA so that they can build the product that they're looking for. I think that's obviously a very unique event in computing history. The number of times that people have regularly used 10,000 node supercomputers, I think, is approximately 0 over history, especially in sort of such a general purpose, high area spanning way. This area, AI and generative models, it's really driving huge advancements in memory capacity, and the requirements for memory bandwidth are exploding. You're seeing today that there are chips with 8 HBM, 12 HBM, and people would like to go to even more density in terms of memory per accelerator. And the memory bandwidth couldn't possibly be high enough for what's needed. And if you look at the challenge here, especially from a networking perspective, HBM, this memory capacity and high bandwidth technology is really fighting for network I/O. There's really not that much shoreline available, and a lot of it's being used by the memories, and there's not that much space left for the I/O. And that's not to mention the heat challenges that are kind of happening. And so when you look at these AI workloads, you really do a time trace and look at where you're spending time. What we find today is in models like GPT-4 and so on, they're very imbalanced between memory, how much time they're spending accessing the memory, how much time they're spending doing computation itself, and how much time they're waiting for networking. And I think ultimately what this drives is very low data center utilization. So you're going to need to buy a lot more compute units than you should actually need to do that number of operations. And it just leaves a lot to be desired. I think there's a lot of work that people are doing to try to fix the imbalance. Every new state-of-the-art neural network that comes out, one of these big LLMs, people are grinding and trying to fix some of the imbalance, but it's a major challenge today. I've heard numbers as low as 10% compute utilization for execution of these state-of-the-art large language models. And what's interesting here is that the cost of networking is really becoming an increasing fraction of data center CapEx. There are a lot of reasons for that, but I think that one of the reasons that the networking cost is being driven up so high is that the amount of I/O bandwidth escaping each chip is growing very, very quickly. And so if fewer chips are able to take up the capacity of a 50 terabit switch, and you're going to need more switches as a result. So this starts to add in terms of cost. We're really needing to be able to link together very large systems, and that bandwidth between chips, between racks, and between rows is increasingly important. So if you look at the cost of AI systems, we talked about 10,000 node AI systems. They're incredibly expensive, and the biggest companies out there are spending billions of dollars to stay in the lead in the space. It's just a massive investment. If you look at doubling, you don't have to double billions in spending too many times before you start running into some major challenges with being able to operate even the biggest companies in the world, given the costs of what AI is going to take. And I think that there's another piece of this as well. You can invest in building these next-gen models, and you can spend money to get that done. But one thing that is really challenging at this point is that the cost per user for running an inference on one of these AI workloads is really driving down cloud margins. We've heard that cost per query is just about 10x for applications like search when you use these large language models. So it's something that the whole industry is looking into and trying to figure out, how do we reduce these costs and how do we get this stuff under control while still being able to grow these AI models, because we know we're not at the end of the road for how big these things can get and how impressive they can be. So my background is in physics, so I care a lot about Dennard and Moore scaling, Moore's law, and we've got some interesting data here on the right that we'll talk about. But at a high level, we're getting a lot more transistors with processor nodes, with process nodes, but we're not able to use them. And the reason is that the power per chip is really getting out of control. When I founded the company about 6 years ago, chips were at 250 watts, and today they're over 800 watts. And I have on good authority that we'll be breaking the kilowatt barrier very soon. And I think that this presents a fundamental challenge in terms of the heat problem. How do you keep these things cool? How do you deal with the thermal density? You've really got to spread these hot potatoes out. At the same time, the challenges with Denard and Moore are they're causing per chip costs to really balloon. There are GPUs out there that are selling for tens of thousands of dollars. It's great from a margin perspective, but I think it's probably unprecedented in computing history. The size of these chip packages is getting increasingly large, and the reason is that you've got to spread things out to get more performance. You're going to need more silicon area, and this is kind of the game that we're playing. And what you're starting to see is very standard is water cooling in the AI and HPC space, and immersion cooling is coming. This is going to drive data center PUE, and it's going to enable even higher thermal densities. So let's take a look at the data here. On the top, we've got package power. So this is the power TDP for the chip packages versus year. So it starts in 2017 and goes to 2023. Not all the labels are on the data points here, but there are some latest gen chips that are labeled from NVIDIA, AMD, Intel. And you can see the trend. Look at the red line. The power is growing definitely super linearly, probably quadratically. And where are we going to be in another 6 years? It's pretty crazy. You start to run up against fundamental physics at some point of trying to keep these things cool. But this is the game that we have to play if we want to follow the AI trend. We have to drive performance forward. The economic power behind driving the performance is massive. It's a freight train that will force progress to happen. At the same time, if you look at how are packages progressing, what does the future maybe look like for computer chips? It definitely looks like extremely large packages. So you can see on the bottom here, the silicon footprint measured in millimeters squared for various chips, and it's growing rapidly. The latest chips are around 2,300 millimeters squared of silicon. Just for reference, a full reticle die is about 800 millimeters squared. So this is just growing very quickly. You can imagine another 6 years and we're at 8,000 millimeters squared and maybe beyond in terms of the package size. So packaging today really defines performance. We're showing some packages here on the right, optical interconnect, very large package sizes, HBM chiplet processors. Every company is really pushing the limits in packaging. How big can it get? How much heat can you pull out of the package? How much power can you deliver? How much current can you deliver into the package? How much I/O bandwidth can you have? These things are all defined by the package design. So a lot of the innovation that's happening in silicon today is really about taking these Lego bricks and scaling them out and trying to figure out how do you get these very large size packages to scale? How do you get the power into them? All these things. And that's really what's going to define how good your computer chip is. It's going to define how much chip I/O bandwidth you have, and so on. I mean, today it's even the case that if you look at how much bandwidth you can pull out of a chip, you're really capped by max TDP for a given package design. And so this is where a lot of the research is happening. And I think that companies couldn't spend enough on solving packaging challenges. All right, so let's talk about silicon photonics as a tool for driving compute performance forward. So if we look at optics, silicon photonics, falls under the category of optics. There's a roadmap for how optics is used in data centers and how it's eventually going to be used in chips. So today we're kind of at the pluggable regime where you have an optical engine sitting at the back of a server, and you have a chip inside the server that's driving electrical signals across the board and into those pluggable optical engines. The distance they're traveling is something like 10 to 18 inches. And it's expensive in terms of picojoules per bit. You're having LR SerDes that are driving these signals, and you're burning a lot of power to get that done. As you try to move to increase the bandwidth and energy efficiency, what really needs to happen is that the optical engines need to move closer and closer to the source of the data, the ASICs. And so in Gen 2, you're looking at onboard optics. So these optical engines live on the PCB within inches of the processor itself. And that's good. but there's something after that, which is Gen 3. Here you're taking your silicon photonic engines, your optical engines, and you're putting them inside the package as a chiplet, for example, to directly receive the bandwidth from the processor over a distance of a few millimeters to ship that bandwidth out. Now, one of the challenges with Gen 3 is that you're still in the shoreline limit, which means that you're looking at the perimeter of the die and how many SerDes you can pack in the perimeter. I think ultimately where this optics roadmap takes us is that you've got your ASIC, your processor, your FPGA, your GPU, your chip sitting in 3D on top of the optical engine. And what's really exciting and important about this type of technology is that shoreline is no longer the limit as it pertains to where you place SerDes. You can have them all over the die, anywhere you want. Of course, you've still got a shoreline limit in terms of those optical fibers that are going to transport data meters to hundreds of meters in distance. But this is really pushing to the limit of what you can do in terms of exporting bandwidth per chip. So the big story with optics is going to be taking it from the back of the server all the way to inside the package, and then ultimately becoming the base layer or the interposer for interconnect. So not that many people have looked into the silicon photonics space. I think a lot of companies are ramping up on this, and I figured I'd spend a few minutes talking about what silicon photonics is, showing you what it looks like. So silicon photonics leverages all the manufacturing infrastructure from CMOS. You can build silicon photonics in a standard CMOS fab. The only thing that's a little bit strange about the wafer is it's an SOI wafer. The industry used those at around 45 nanometer. They're used in silicon photonics because you need that glass layer underneath the transistor device layer so that you can actually guide light. And you can see a cross-section on the top right here of what some fabricated devices would look like. You've got the silicon handle. Above that, you have the buried oxide. This is silicon dioxide. And above that, you have the device layer. So the device layer is where you would have photonic waveguides, photodetectors, transistors, and all of the different active components and passive components that you would want to build. And then above that, you've got the metallization and passivation and everything else. Bottom right here, we're showing a nanophotonic waveguide. So they're about 200 nanometers thick. They're the same thickness generally as the device layer. And then they're about 400 nanometers wide for a single mode waveguide. As you make waveguides bigger, they actually become multi-mode, and you start to see multiple nodes in terms of the electromagnetic field. Okay, great. So at an abstract level, we're using, CMOS processes. The biggest foundries in the world can build this stuff. But what does silicon photonics really look like? So what we're showing here is an example of a random photonic network. This isn't a useful network, but it's an example of what this stuff looks like. One of the things that's really interesting in the field of silicon photonics is that the schematic that you would draw on paper to describe what you do pretty much looks like the actual circuit on silicon. So here there are a bunch of devices called out. Here's a grating coupler on the bottom. That allows you to couple light into and out of the chip. It shines the light vertically out of plane. In front of that, we've got a Y junction. It's effectively a device that splits the light field 50-50 in power between the left and the right half. In front of that, a ring modulator. So this is a device that can be used to do multiplexing or demultiplexing. And it can also be used to modulate electrical signals onto the optical field that's propagating through the waveguides. Above that, we're showing a crossing. One of the interesting things in the field of photonics is that you've really only got one, maybe two routing layers. Imagine building an entire CMOS chip where you only have one metal layer. That's kind of the situation that people have to deal with in silicon photonics. The fortunate thing, though, is that you can build crossings and they're not a short when you're looking at optical fields. And so that's a crossing device there. And then how do you get data from this optical domain back into the electrical domain? Well, that happens with a photodetector. Very boring looking. If you look at them on a chip, they're kind of a rectangle with a bit of a pyramid on top. But this is what silicon photonics kind of looks like. So some more photos of this stuff. On the left, this is a traveling wave Mach sender interferometer. That's a lot of technical jargon if you're not in the photonics space, but what it does is it takes signals from the electrical domain and transports them into the optical domain. And then you can route that over waveguides and ultimately into optical fibers for communication. Top right here, we're showing grating couplers. So this is an example of one way that people couple light into and out of chips. They look like sort of a fan. And then below that, this is what a silicon photonics enabled chip looks like. You've got some optical fibers coming out the back and a little window where the fiber attach happens on the top here. So just in case you've never seen it before, this is what it looks like. And just to give you a sense of scale, on the left here, what we're showing is an optical fiber. So optical fibers form the backbone for most long distance communication, if not all at this point. They can have extremely high bandwidth. Many, many terabits per second can be handled by a single fiber. They're made of glass, and this is kind of the backbone of the internet and a lot of networking. If you compare the scale of those things to nanophotonic waveguides, there's about a factor of 40. So there's a huge density difference between optical fibers and integrated waveguides. And that ends up being really important when you look at how are we going to continue to drive package body size, how are we going to drive up I/O bandwidth, beachfront density, and all these things. Photonic waveguides are extremely small. All right, so let's take a second and talk about co-packaged optics, CPO, and some of the challenges. I think there's a lot that the industry can do to drive this stuff forward. I think we're going to cover some of those pieces here, but it is a relatively nascent area, and there's going to be a lot of investment required to get to massive scale. So there are a few different challenges in the space for silicon photonics, and I think these are top of mind for me and most people who are actually building this stuff. One is packaging. It turns out that getting optical fibers that are relatively large rods of glass attached to a silicon chip is very tricky. We'll talk in a bit more detail about why that's the case and why it's something that the whole industry needs to work on. The second piece here is in-field repair. Imagine that you spent, all the investment required to build and then ultimately sell, and the customer's got your chip, it's got fibers attached, and then one of the fibers breaks. If those fibers are glued to the chip, you've effectively just lost a port. You might have to throw that chip away. So how do we get to a spot where you've got in the field repair? How do we get to connectorize silicon photonics and the method for how we take signals that are on the die and get those into optical fibers where they can be transported long distances? I think lasers are a major challenge in the industry. Lasers, I think are one of the most challenging devices out there. They have lots of limitations. The packaging is quite ancient looking, and there's a lot of work to do on that front. And I think one of the other challenges in the CPO space is the fact that once you've built a CPO-enabled chip and you wire it up to the rest of the chips, maybe in the server, in the rack, in the row, you're at a fixed topology. You need someone to go grab those cables, unplug them, and plug them somewhere else. And that's a major challenge. So let's talk about optical fiber attach. This is actually what it looks like. You can see, optical fibers being dropped onto a silicon photonic die. Ultimately the process looks like this. So you take optical fibers, you bring them into your silicon photonics die. You need to dispense adhesive, and then you have an ultraviolet light that cures this assembly for 10 minutes plus, and then it's hardened. There are lots of challenges associated with that adhesive and how you get that done, and that's something that people are constantly optimizing. If you look at different techniques here, there are V-groove based approaches, there are grating coupler based approaches. They all have their own challenges, and I think that one of the most profound sort of issues in this space is how do you get advanced packaging that is compatible with optical fibers? You have to deal with reflow, You have to deal with a lot of standard processes that you would use for electronics that are really going to damage these optical fibers that you get attached to the chip. You have to deal with dangling fibers, things like this. So there's a lot of innovation that's going into how do you enable photonic packaging, and how do you make sure that these fibers are reliably attached and at low cost. So talking about a sense of scale here, how many fibers can you actually get attached to the chip? Practically, maybe, if you just look at ratios of beachfront and fiber pitch, you could get to a couple hundred. Practically, you could only get 64 or so fibers attached to a chip. So that's not a lot of lanes. Optical fibers are going to be a major challenge in terms of scaling up the I/O counts and the fan out from a single chip that's enabled by optics. And the reason is that you're taking these glass rods and having to glue them to the silicon, and then you need that to be reliable over temperature and everything else. So optical fibers and optical fiber packaging is one of the central challenges in this space. The next piece here, kind of visualizing what the wiring diagrams look like for an all-to-all. Imagine this case. Imagine you're in a data center, you pull out a rack, maybe it's a DGX box, and you see 8 processors inside. Imagine we're in the future and they've got optics there. If you wanted to link that up in an all-to-all configuration, you're going to generate sort of rat's nest spaghetti of optical fibers just to make those links. There's a lot of loss associated with the connectors, and it's very hard to service these kinds of systems. You scale that up not only to your servers, but to the rack level and then to the row level, and the wiring and manageability of this optical fiber problem and the number of fibers involved, it's very tricky. So there's a lot of work that needs to go into that. Typically, people use fiber looms to do the mapping. So, maybe you want to wire up an all-to-all. You basically build a fiber loom that contains all the connections and remaps everything, and then you plug the chips into that. So you're taking up rack space to get this done. And, it's just, that's area that's not doing computation or making money for you. All right. So lasers, a good joke from one of our VPs of engineering. They have wings, but they do not fly. They're one of the most challenging devices in the space, and they're really going to be the limiter for how fast you can go with silicon photonics and at what scale, how many devices you can pass through. And I think there's a massive amount of work that's going to need to be done to take what exists today, these sort of butterfly form factors, eventually pluggables and so on, and get them into a sort of form factor that is cheaper, has much more optical power and so on. And let's talk a little bit about performance characteristics for these devices. So today you can get maybe 8 colors, so 8 wavelengths lasers. You can buy these from various vendors. They have about 50 milliwatts per laser, and there's just 8 of them on that chip. So if you're going to need 32 lasers, you're going to need 4 of these laser modules to get the work done for you. And they typically look like this butterfly form factor on the right. So, right now there's really too many laser modules required to power the I/O of just one chip that's silicon photonics enabled. The packaging is very primitive. It doesn't look anything like the state of the art that happens in the ASIC space. There are very limited thermal budgets. If you take a laser and you put it on a hot plate and you turn the dial, what you're going to see is that the brightness falls off with temperature. And so lasers typically want to be running cold. Ideally, they'd be at 25 degrees C. They really need to operate at something like 60 to 80 C. And the efficiency, the wall plug efficiency drops off pretty severely as you increase the temperature. So practically, when you're looking at a laser efficiency, you're going to end up at numbers like 5%. So you put 20 watts of electrical power in to get 1 watt of optical power. There are not many things in our industry that are that inefficient. There are challenges associated with getting optical fibers attached to these laser chips. They have very small mode field diameters. What that means is that the spot size, like how big is the spot, the light spot coming out of the chip, it's very, very small. It's typically a fifth of the size of the optical fiber spot itself. And so you get a lot of loss there. There are challenges associated with getting those fibers onto the laser. And there are a lot of drive components that go into controlling these lasers, delivering power to them, monitoring them, and making sure that they're functional. Not to mention, failures in the field and being able to detect that and so on. In addition, color multiplexing, getting all those 8 colors into a single fiber, it's generally not available in a monolithic die. And so you start having to do multi-chip packages that are generating the light and then multiplexing it and then sending it out of a fiber. So needless to say, I think there's a massive amount of innovation that can happen in the laser space and that needs to happen. And we're looking very carefully at how to scale up laser counts into the hundreds so that you can really get to the sort of bandwidths that we're going to need over the next 10 years. I think it's well understood at this point that chiplets and co-packaged optics are needed. People are all working on this problem. Some interesting things to note about chiplets as we all go on this path and we go to bigger and bigger chiplet packages. The more chiplets you have in the package, the higher the energy and latency that you will need to traverse from, let's say, the top left chiplet to the bottom right. Every hop's going to add a picojoule per bit. It's going to add another unit of latency. And you start to get to a point where you're burning a lot of power on interconnect for linking these chiplets up. And you're waiting a lot of time for that. And that's slowing down the computation ultimately. When you look at what's happening with the chiplet XPU and CPO space, what we're finding is that optical fibers have very low beachfront density. You need to be able to pack as much bandwidth as you can per fiber. You can do that with more wavelengths. So you have maybe 8 colors, eventually 16 colors. And ultimately, these CPO-based platforms are very static. You plug them in, and you kind of get what you get in terms of the network topology. There's another piece to this puzzle as we're looking at bandwidths like 4x 1.6T. You start to look at the top of rack infrastructure and these switches. They're at about 50 terabit per second. You're only going to need about 8 of these CPO-enabled chiplets to saturate the bandwidth of the entire 51 terabit switch. So the compute to switch ratio is poor. And what that means is you're going to be driving up costs for the networking. You're going to have a lot of bandwidth flying out of these chips, and you're going to need a lot of switches to intercept that and route the data and link everything together. I think one of the biggest challenges among the many in this space is the supply chain. Really the question is the photonics supply chain ready to support the growth that it's about to see? Every major company out there that's building accelerators is looking at silicon photonics, and the volume that could land on that supply chain could be quite massive. A lot of the people in the space that are developing the innovative tech that's needed are with boutique companies. These are not large corporations, and there's a lot of work that's going to be needed to get this stuff to scale. All right, so there's all the challenges in the space. As with all new technologies, and new ideas are needed. And now we're going to talk a bit about the work that we're doing at Lightmatter and what we see as the future going forward. So just to recap some of these issues, per chip performance must scale. Yes, you can sell more GPUs and CPUs and scale up these systems, but it has to be the case that we continue to drive the performance of each chip every 18 months, every 2 years, up and to the right. And so that's just a requirement. Scale out's not the whole picture here. Chiplet packages are only going to get so big. So if you're going to use that as the only vector for getting performance to scale on a per chip basis, there are limits, latency, power consumption to getting that done. So with 10,000 GPU clusters becoming commonplace, your I/O bandwidth, the amount of interconnect bandwidth between the nodes, has to scale significantly, and you have to keep the latency very low so that these small operations that have to be performed and then synchronized are actually resulting in a system that you're adding a unit of compute and you're getting a unit of performance out of the system. There are major shoreline limitations on bandwidth with technologies today. The perimeter of a piece of silicon there's a lot of competition for that area. It's being split across HBM, but also I/O, whether it's optical or electrical only SerDes. CPO is going to grow the package footprint. If you look at traditional in package chiplet-based CPO. So you're going to have bigger and bigger chip packages driven by traditional CPO technologies that are just, side by side with your chips. And they're also going to be limited by beachfront, just like existing technologies. Fiber management, the static network topology is a major challenge. And I think we've seen a lot of people at the conference over the last day talking about optical circuit switching. I think it's increasingly viewed as a path towards ultra high performance and configurable interconnect. And I think that it's a very important piece of technology that'll make its way into the market. So how do you address all of these challenges in one pass? Here's our vision. Just let this play for a second. So this is passage. This is Lightmatter's answer to networking. You've got the lid, you have an array of ASICs on top, you have passage, the silicon below that, and then you have the organic substrate. I'll let this play one more time so people can have a look. You're able to integrate arrays of chiplets and full-on chips and interconnect them optically, single hop between any of the chiplets in the package. And then the optical fibers are used for transport between passages, whether they're in the same rack or in different racks. And this is what we think is going to be very important for enabling large body sizes, low latency, ultra high bandwidth, and continuing to scale single processor performance as well as system level performance. So taking a look here at a still of passage, passage is diced from a 300 millimeter wafer. So in this example, you can see there's maybe 10 or so passages per wafer, given the size of the square here. So they can be as big as the entire 300 millimeter wafer or as small as a single tile. And what's interesting about that is you can basically create a dicing plan. And depending on what you cut out, maybe it's a 2x2, a 3x2, whatever, you get a different SKU for the product. We generally work with SerDes, the chips that are sitting on top. They're purely electrical, they're off the shelf, no change to any silicon that you've got today. And their electrical interfaces communicate directly with the optical modulators and components inside of passage with no change. We're looking at UCIe interface. We think that's going to be important going forward. Today, SerDes-based technologies are how we do communications with passage. And we're really excited about this technology. So let's take a look at the cross-section of passage and see what's going on inside. We've got passage tiles. This is the repeated unit on passage. A tile could be bigger than a single reticle, so it could be bigger than 800 millimeters squared, but ultimately that tile is stamped out across the wafer, and you take your ASICs and HBMs and so on, and you do chip on wafer packaging to place them on top. There's electrical stitching, so not stitching, but electrical interconnect for linking HBMs, for example, to ASICs. And then, when you're in your ASIC and you want to send data between tiles on passage, your SerDes sends a signal to the optical transmitter that passes through a waveguide and an optical circuit switch and routes ultimately to a SerDes on the other side on another chip. You can also decide to route to an optical fiber array to get data off the platform. Power delivery, it's about 700 watts per 800 millimeter squared area for TSVs. And the cooling solution for this platform, it depends on the ASIC TDP, but typically you're going to see water cooling. So we can take a look at the photonic data path here and some of the modulation formats and so on. Top view, let's say there are 8 ASICs and they're all communicating, in this case, using 8 colors and linking this whole platform together. So the interface goes SerDes to the photonic transceiver, which for us is a micro-ring resonator. That heads into a multiplexer. And now the data is in the waveguide. So we can look at what's happening after that point. So this diagram here is summarized in the bottom left, SerDes to transmit to multiplex. Now you're in the optical circuit switch. So what happens here is we're able to dynamically configure the waveguide interconnect between all of the chiplets on top of passage and to all of the fibers that leave passage. And so you pass through the optical circuit switch from one ASIC to another ASIC or out the fiber. you hit a demultiplexer, taking those 8 or 16 colors, and you spread them back out into spatial modes where they're received at a photodetector, and then you have a transimpedance amplifier, and that directly interfaces back with the SerDes. So ultimately, it's SerDes in, SerDes out, and there's a bunch of optical stuff that happens in the middle. Today, we look at 56 gigabit per second and 112 gigabit per second PAM4 encodings, 8 lambda, 200 gigahertz wavelength spacing for the laser. At 56 gig, that's 900 gigabit per second bidirectional. And at 112, you're looking at 1.8 terabit per second bidirectional. The nice thing about 56 gig encoding NRZ is that we can operate with no FEC. If you're looking at scale out, if you're looking at low latency applications, not having to deal with the latency overhead of FEC is really valuable. But if you're okay with it, PAM4, you can get a lot of bandwidth per fiber, and the error rate, will increase, but meet the sort of specs that the industry expects for that type of link. So passage is really big. What makes it possible? It turns out that we've got both optical waveguide reticle stitching and metal stitching. And when light crosses those optical waveguide boundaries that span between 2 reticles, the loss is almost 0. It's about 4 millidB or 0.004 decibels of loss. So there's a lot of work that goes into making this kind of thing possible. And it's one of the core technologies that allows you to scale a platform up to the sizes that are going to be needed to drive single chip performance through technologies like passage. So let's talk about optical circuit switching. There's been a lot of conversation on this technology, but nobody's really driven into how it works with silicon photonics. So let's do that here. There are fundamentally 2 kinds of optical circuit switch components. One, you have a spatial mode router. So this is allowing you to take waveguides and map where they're going onto another waveguide. That's typically done with a Mach-Zehnder interferometer. What you do is you have light at the input, you have an optical phase shifter sitting between 2 beam splitters, and by setting the phase using a voltage on the phase shifter, you can control how much light comes out of the top port P1 versus the bottom port P2. If you think about this in a binary sense, you can set the phase on the Mach-Zehnder to route light either to P1 or to P2. And what it's doing is it's giving you a 2-port switch, 2 ports in, 2 ports out, and it can do all of the mappings in between. On the right, we're showing a ring resonator. So what this is it's a spectral mode router. So let's say you've got 8 colors traveling in a waveguide, and you want to spread those back out. Well, you're going to use a ring resonator or some type of wavelength-dependent device to get that done. And by applying a voltage on the phase shifter inside of this ring resonator, you can allow light to either pass by the ring off resonance, or to travel into the ring and actually be routed into another waveguide. So now you're able to specifically choose wavelengths, pull them out, and put them onto different waveguides so that they can be used with Mach-Zehnder interferometers to do the spatial routing and mapping of waveguides to other waveguides. So those are like the fundamental building blocks that go into optical circuit switching. Let's take a look at how we use it in passage, at least inside of a passage. So here on the left, we're showing an all-to-all configuration. This would be programming, big arrays of these interferometers and resonators to implement a graph that connects the 8 chiplets in an all-to-all fashion. You can program that every millisecond or so with passage. So at 1 millisecond, you're at all-to-all configuration, and the next millisecond, you've switched to a 1D ring. You've changed all of those components inside of passage, and now you're actually sending the bandwidth in a ring between the 8 processors. If you look at one of the links, now you have 3 times the original bandwidth. The number of links is conserved. And so by having fewer edges, you've got more bandwidth linking the nodes. And so we think this is a really important technology. If you look at the runtime of algorithms, they're strongly dependent on the interconnect. And by having the ability to set the interconnect, you can have a very big impact on application runtime. So let's take a look at inter and intra-passage optical circuit switching. So in the animation on the left, we show a 1D ring transforming into an all-to-all type interconnect. And then you've got 4 passages that are all communicating and dynamically changing the interconnect topology there. So this is, if you think about passage as a component and then as arrays of passages, this is how the programming happens. Really big impact on application runtime. But another piece to think about here with optical circuit switching is that what we're able to do is completely reroute a set of input fibers to a set of output fibers. And this changes the game. If you look at CPO-based technologies today, once you've wired the thing up, you kind of just have what you have. With passage, you can completely reprogram how all of the optical fibers are interlinked. And so your network is dynamic now. You don't need someone to go in the data center and plug things in a different way. You just send a command to passage, and passage will reshuffle the network of all the optical fibers. Looks like we're having playback issues with the video, so I'm going to skip that. We had a near infrared microscope video of optical circuit switching, but we'll skip that for now. So this is a device that we built a few years ago. It's our first generation passage, and it's the world's first photonic wafer-scale interconnect. We figured we'd start things off by doing the hardest thing you could imagine doing. What we're building today is a bit different, but we were successful in the program. So on the left, you've got a 300 millimeter wafer, and you can see cut into that wafer is a 200 millimeter by 200 millimeter chip. So each one of these repeated structures is called the tile. We can zoom into the tile, and you've got, in this case, we started out using integrated lasers. Today, we use off-chip lasers for serviceability, and because of the fact that the temperature of the chips that are sitting on top is very high. But this just shows you that you actually can integrate everything in one go. So zooming in here, you can see the lasers, you can see the transmitters and receivers, and in the middle, you can see the optical circuit switch network that allows you to reroute the network topology for the platform. Bottom left here, you're seeing the optical waveguides. So this is a scanning electron microscope image of what the waveguides look like. They're very small. They have about the same pitch and width as electrical traces on an integrated circuit. So this platform was about 48 terabit per second, contained 6,000 data converters, 6,000 Mach center interferometers, 150,000 photonic components. It was programmed over JTAG, sort of a debug interface, and it worked for that platform. But really a massive chip, and shows you the limits of the scale of these things. In terms of bandwidth, you can go much, much higher than we did in the first pass, but 48 terabit per second isn't too bad. So if we look at the switch component that was included in that chip platform, the amount of time it takes for the switches, the optical circuit switch component itself to change is about 7 microseconds. So it's pretty fast. And we think that there's a path to getting this down to nanoseconds. So rather than viewing it as, okay, you bring down the system, reprogram everything, and now you've got a fully different network that you're working with, there's a path eventually towards switching these things in nanoseconds and dynamically routing where the data is going. But I think that there's a huge amount of value, even at the sort of timescales that people are looking at today. If you look at what Google's done with their optical circuit switching technology, being able to carve out broken processors, being able to divide the cluster up among many users, even in the microsecond timescale, there's a lot of value to be had with circuit switching. So at Lightmatter, we're looking at a lot of different applications and working with customers on different ways to use passage. There's the obvious sort of use case. You think about pools of accelerators, pools of memory, and being able to dynamically dial up the ratios of compute and memory. You can also look at cloud use cases. For example, you've got 4 users that are sharing a passage chip with, let's say, 16 processors on top. Using the optical circuit switching, you can dynamically allocate how many processors each user gets every millisecond. And the exciting thing about that is that you physically disconnected the optical wires. And so you have air gap isolation, and you're able to drive up utilization of these processors for the clouds, which is a key metric for them. There's a lot more that we think about in terms of what passage can be used for, but those are just a couple points. So just to leave you here with a point, what is passage? Passage is a 3D co-packaged optics technology combining self-contained active optical interposer. That self-contained point is extremely important. You don't need to go insert a bunch of photonic controllers inside of your 3 nanometer chip to be able to use this. It's fully self-contained. You're only driving SerDes into Passage, and on the other side, your SerDes is receiving it. Passage uses advanced packaging technology and state-of-the-art light sources to profoundly increase the capability of ASICs. We're going to enable ASICs to get much, much bigger, drive single chip performance and system level performance, improve bandwidth density, increasing serviceability through some of the technologies we're working on with pluggability, reducing picojoules per bit. You can't possibly have a shorter interface than a single bump between your SerDes and the Passage optical transmitter, and ultimately reducing package size compared to CPO-based technologies where you've got perimeter-based CPO chiplets that are growing the size of the organic and increasing the cost of the solution. So with that, I'll thank everyone and thank you for the invite for this keynote, and happy to take questions and to talk more.
Wow, that's fantastic, Nick. Thank you so much. The number of questions is really quite high. I'm going to start with the questions that are on Zoom because they'll go away, and I'd ask you whatever questions we don't get to that are on the Slack channel, you can go in and answer those later.
Yeah,
So,
and just a reminder to people, don't use sparkling water to quench your thirst in a talk. Doesn't go well. That was rough.
Okay, question number 1. Gen 3 photonics evolution seems interesting. Can you comment on 1, power dissipation of high-powered electrical die affecting silicon photonic die, and the AVDD placements all over the die when SerDes are everywhere?
So the power consumption of the ASIC that's driving signals into a Gen 3. So let me go back to Gen 3 here. Let's look at Gen 3. All right, so Gen 3, we're talking about 2.5D chiplet in packaged based technologies. So today chips are operating at about 100 degrees C. Lasers really don't like to be at that temperature. So if you've got on-chip lasers, the efficiency drops off a lot. Your picojoules per bit for the link is going to be increasing. I think that...
I'll interrupt you. He says, sorry, question is about Gen 4, not Gen 3.
Okay, yeah, so about the power consumption of the ASICs on top. So we're using TSVs at Lightmatter. We can deliver, about 700 watts per 800 millimeter squared up to that chip. So we don't see a big limitation on getting power to those chips. Most of the optical components are extremely well behaved up to 100 degrees C, so there's not much of an issue there. But there's a lot of engineering that goes into just making sure this stuff works over the full operating temperature range and making sure you can get all the power delivery done, whether it's placement of voltage regulators or design of the TSV layout itself. And there's a lot of thought that goes into that.
Okay, thank you. Next question. Can you compare your OCS to the Google MEMS mirror-based OCS? Pros and cons.
Yeah, so the Google MEMS mirror-based OCS is actually taking light and bouncing it between mirrors and between these little MEMS devices that move X, Y, Z. They're not able to displace from the surface, but they can basically tilt. And they're aiming these little mirrors at each other. MEMS is notoriously hard to yield. And if you manufacture, let's say, 160 by 160 switch, the yield might only be that you get 130 by 130 in terms of usable working switch ports. So that's a challenge. MEMS also has challenges in terms of how fast you can switch. It's not solid state, and so you've got shock and vibe. You've got other reliability concerns. The size of it with these sort of MEMS mirrors is significant because you actually have to let the beams propagate in the air between the chips to do the remapping of the optical fibers versus what you do with integrated circuits and solid state photonics, where we just apply voltages to silicon effectively, and we're able to dynamically reroute the light fields. So you're going from sort of a free space optical system to an integrated circuit. I think there's a lot of cost advantages, area, weight, power, and so on, to doing it with an integrated technology like Passage.
Mm-hmm. What is the size of the OCS?
Well, it depends on the port count. So, we see paths towards 512 by 512 port switches. There's a lot of packaging work that goes into making that kind of thing possible. But if you think fundamentally about what Passage brings to the table, it's reticle stitching, large format die, and a lot of the optical circuit switching technology. We think you can get really big with these platforms, and we think you could build optical circuit switches that are routing petabits per second of data. And I think that's going to be in a regime where it's extremely useful for AI supercomputing and HPC and low latency.
Super, super. What do you think of integrated laser? Hold on, somebody just changed it. What do you think of integrated laser? Is it the future trend, or do you see the laser source staying external?
Well, I think serviceability is key here. So external lasers, you can throw them away and plug in a new one. I think that's pretty important. The other piece is that the physics of traditional lasers works against you with the operating point of ASICs. ASICs want to be at 100 degrees C, and the laser wants to be at 30 degrees C if it can. And so putting it inside the package in that very aggressive thermal environment drives the efficiency down. It's hard enough to get enough optical power to power 50 terabit switches. If you're going to go ahead and put that laser inside the heat bath, you're going to need even more lasers to get it done. So I think new technologies are needed. There's work on quantum dot lasers. I think that's exciting. There are other types of light sources, LEDs and so on, that have interesting thermal properties, but they have their own major sets of manufacturing challenges to getting them to market. And light sources are a big area that needs innovation. I'd love for them to be on chip, but there are a lot of reasons why it's not going to happen right now.
Very good. What is the shortest distance between ASICs next to each other? And what is the achievable picojoule per bit for them to signal to each other?
Well, you think about the limits. If you're talking about sending signals across 2 millimeters, you probably shouldn't be using an optical link. If you're sending on that kind of distance, you should use electrical. Now, where it gets interesting is where you're hopping multiple chips. And I'll tell you, with CPO type technologies, these 2.5D Gen 3, typically there are something like 5 to 7 picojoules per bit. At Lightmatter, with our 3D optics, we're getting fractions of that, significantly lower.
Okay, fantastic. Somebody wanted to know, is your latest product in production?
I wish I could say all the stuff we're up to. You're going to start seeing Lightmatter passages all over the place over the next 18 months. And I'm excited about that. Good.
When do you route the light using a Mach-Zehnder interferometer, and when with a ring resonator? You mentioned those two different approaches.
Yeah, Mach-Zehders are used when you've got maybe a bundle of colors that are all traveling in the waveguide, and you want to send that whole bundle somewhere. That's where you're going to use a waveguide router like a Mach-Zehnder. When you need to separate the colors and then route that, you're going to use a combination of rings to pull the colors apart inside the waveguide, and then Mach-Zehders to actually route where the waveguide's going. So together they form a toolkit for mapping waveguides and colors wherever you need them to go.
Got it. And how do you compare how do you compare the Lightmatter OCS with that from Pilatus?
I'm not familiar with Pilatus OCS, so I don't know.
Okay. At some point, please discuss 3-5 photonics in addition to silicon photonics, and especially how to combine the two.
Well, the lasers that are used with silicon photonics are mainly 3.5 based lasers. There's a lot of exciting work that's been done to integrate films, 3.5 films onto silicon photonics processes, so you can have modulators, you can have laser sources, amplifiers, all built into the platform. I think that's all exciting. As I mentioned, though, with 3.5's lasers, there's a big temperature problem for the light source. And so integrating them with silicon photonics can be a bit tricky in 3D applications and even 2.5D applications. There's been great progress in 3.5s on building photonic systems. They're used and deployed in many ways, but it's hard to beat the scale you can achieve with silicon photonics and the silicon foundry platform. There's trillions of dollars invested, and the volumes, I think, are unbelievable. And 3.5s aren't quite in the same spot when it comes to the manufacturing technology.
Well, that's great. I think you did a marvelous job of answering all the questions. I think we got through all of them. You can check the Slack real quick to see. Fascinating presentation. Thank you very much.
Thank you.
Okay, next up for us is one of our sponsors, right? We'd really like to thank Arista for this. Hardev Singh is a director of product management at Arista, responsible for the product management of the data center and campus product lines. He has been at Arista since 2021 and has over 16 years of experience in networking technology, having spent 13 years at Cisco in both product management and system engineering roles, where he was part of the team that developed the Nexus 9000 data center switches, transceiver modules, and Catalyst 4500 campus switches. So welcome to you, Hardev, and please take it away.
Thank you, Alan. Sound check, are you able to hear me okay?
Sounds great.
My slides are up?
Yes, sir.
All right. So good morning, good afternoon, good evening, everybody. I have 10 minutes, so I'm going to do my best to get done with my slides. I'm going to be basically talking about, the trends in the data center, how's the 400 gig speed, in terms of adoption, and then, looking into 800 gig. So let me get started. Data center switch shipments continue to grow. We all know, with the splurge of applications now, AI, bandwidth pretty much is doubling, every 2 years. So that puts the onus on the network to kind of, keep up to the growing bandwidth demand. If you kind of look at some of the, trends that are, that we see in the data center and kind of divided that into two segments, we have the enterprise, the traditional enterprise, they are pretty, happy at, 10 and 25 gig compute, with 100 gig uplinks. Though there is a section of the enterprise customers who are now actively looking at AI. So you will see a mix of, the traditional compute with 1025 gig server connect, and also some HPC and AI kind of workloads in the enterprise. On the hyperscalers, the cloud guys, they're always hungry for bandwidth, right? So they were at, 100 gig, even 200 gig on the NIC. And there is, heavy deployment of 400 gig in the hyperscalers. Now, I mean, we all know with, AI, generative AI, there is a big focus on not only the tier 1 cloud hyperscalers, also, tier 2 cloud providers to build out, these AI clouds. And once you build an AI cluster, you kind of the baseline table stake speed is 400 gig, and if you had 800 gig ready today, they take that, right? So that's kind of how the trends we see on the hyperscaler side. On the DCI, data center interconnect, we see active deployment of 400 gig, 400 gig ZR and ZR plus are almost kind of groundbreaking technology. So customers are adopting the ZR and the ZR plus standards. So what's driving growth, kind of iterating the same point I made, from 2006, it was really compute driving the growth. 2010, we had compute and storage, and now it's, it's heavily focused on, HPC AI, right? So that's kind of top of mind for the customers today. It's important to kind of see how the speeds are moving. And we're in 2023, and I look at this as this is very important kind of, to see how these speeds are evolving, and that kind of directly translates to the data center products. So we're in 2023. What's interesting, quick points here is that, 25 gig is kind of taking over, 10 gig. Though all the products we have today are 1025, so it's kind of hard to make the distinction. But 25 gig is going to stay, for a long time, and has a big part of the ports in the market. 1 gig is steadily coming down, but it's still going to be relevant for out-of-band management. 100 gig is going to have, high volume. Now, 100 gig plays on both sides. Today, it's kind of a derivative of 25 gig, 4 times 25. But you see here on top, the red, which is 800 gig, which is kind of going to take off very fast, right? And that's completely attributed to, AI and AI clusters. Now, 800 gig in its first generation is also 8 by 100. So, the 100 gig, blue bar that you see here is, it's got a mix of 4 by 25, 2 by 50, and then I think from 2024, bulk of it will also be attributed to 800 gig. 200 gig was small, continues to stay small, it's adopted by, 1 or 2 large, hyperscalers, but 400 gig is also, going to stay steady, right? So it's in high deployment, starting to ramp up, and then it kind of stays consistent. Same slide, if you kind of, move that into, ASPs or revenue, obviously the ASPs are going to be high for the higher speeds. So around 24, 25, you'll see the bulk of, the dollars are going to be spent on 400 gig and 800 gig, right? Software staying consistent, and then your 100 gig kind of taking the lower end of the dollars spent. This is kind of a question that keeps coming up. Hey, is everything moving to the cloud? I mean, not really. The top 5 US cloud providers, will continue to grow. Your tier 2, tier 3 cloud providers will, are showing growth, will be steady. The legacy enterprise, we see that that's kind of going to come down. This is a graph from 650 Group. But what's also going to increase is your private and hybrid cloud, right? So there's growth in private hybrid cloud. The hyperscalers, both Chinese and US, will continue to grow, and then your tier 2 and tier 3 cloud providers as well. I like to talk about this slide because it kind of directly translates to the data center products. I was talking about the cloud trends. Yes, they're actively moving to 100, 200 gig NICs. On the front end, I'm not talking so much about the back end, which is the AI cluster. The enterprise, if you see, in 2023, so the next 2-3 years, bulk of the server NIC speeds are, going to be 10 and 25. So 25 is the gray color is 25 and the orange is 10, right? But because the enterprise market is so large, right, we also see the blue and the dark blue bars growing pretty fast, which is telling you that even within, the enterprise, the medium and the large enterprise, there is adoption of, applications, or customers are building out, fabrics that require 100 and 200 gig, which now, is mostly AI clusters. Again, in terms of NICs, we have to look at it from, different verticals, right? So in the enterprise, right, 10, 25 gig is predominant today. And what we're seeing is this new generation of NICs, which are 50 gig PAM4 based. What I'm seeing is most popular with customers is the 100 and 200 gig NICs, based on 50 gig PAM4. So you have 2 by 50 to get the 100 and 4 by 50 gig PAM4 to get the 200 gig. And then we've kind of, announced a bunch of next gen products to, which would be the top of rack and spine for these 50 gig PAM4 NICs. What I'm not showing on this slide are, the NICs needed for the GPUs, the AIs, right, which are today at, 200 and 400 gig, right? So either it's 2 by 200 or, single 400. And these are your, NICs from, Mellanox, the ConnectX series, or, Broadcom or Intel, right? Those are the ones that are kind of dominant in the market for AI NICs. So, my talk is about 400 gigs. So what customers are are deploying and continue to deploy in 2022 and this year are products based on 3 different silicons that we use, right? The Trident 4, which is a 12.8 terabit chipset, the Tomahawk 4, which doubles to 25.6, so you get like a 64 port 400 gig switch, and then on the deep buffer routing side you have the Jericho 2C+. The next generation chipset, which are basically 800 gig, that would enable 800 gig, would be the Tomahawk 5, which is a 51.2 terabit chipset, and then Jericho 3 with Ramon 3 is also chipset that we are building products for 800 gig. So sometime next year, depending on different products, we will be releasing 800 gig systems for your data center spines, super spines, as well as leaf spine networks for AI clusters with Ethernet. 400 gig, like I said, is deployed in volume today and continues to grow. And we at Arista have bunch of products, all the way from 1RU, 2RU boxes, going to these 4RU systems that are semi-modular. Customers get to have the flexibility to choose even lower speeds, 100 or 25 gig, as well as 400 gig. And then if you really want to go, high density 400 gig, you could go with the 7800 series chassis that can scale up to 576 400 gig ports. Other than switches, I mentioned ZR. So this is again groundbreaking technology. Customers, at the 400 gig speed can just plug in, 2 ZR optics on either end, and you could connect up to 120 kilometers. And then with ZR plus, for long haul DWDM, you could go into thousands of kilometers. So systems are important. Optics are equally important because they are also going to command a lot of wallet share from customers. So if you look at how the optics evolved, at 100 gig, you have QSFP28, we started with the 4x25 gig SerDes, and then now we have, single lambda based 100 gig optics as well, right? On the 400 gig, the SerDes speed is 8x50, and then we have products which are native 400, either, in a single 400, or even you can break out with 4x100. 800 gig optics are going to, be using the 112 gig SerDes, right? So the 800 gig switches or routers that we'll be building will come with 100 gig SerDes, right? And then you have the optics, 800 gig optics, which initially are going to be really used as 2x400. But what's unique about the 800 gig speed is you see the electrical speed, which is 112 gig, and the optical speed is also 100 gig. So this kind of, leads into the next couple of slides, which gives the opportunity to, for us to look at linear drive optics, which are basically, go here, which are basically optics, that do not have a DSP, right? And what that does is it kind of lowers the power because you don't have, an extra chip in the optic, and also reduces power. So for customers, that is very important. And our kind of analysis shows that, customers can expect almost about 25%, power reduction by going with the linear drive technology. It's still kind of, in the development phase, but we hope to see, the linear drive optics products sometime next year. So yeah, so in summary, the linear drive pluggable optics, have kind of the same power that co-packaged optics, provide, and then it really offers significant cost reduction for customers, both in terms of the cost of the optic, as well as reducing power, which is kind of the most important aspect for customers building AI clusters, because they are restricted by the amount of power they can have in a rack. Yeah. So that's all I had. Alan, I don't know how I did on time. I'm happy to take questions.
Well, very good, Hardev. Thank you very much. We're gonna push the questions over to the Slack channel, right?
Okay.
So if you have questions for Hardev, please post them in the Slack channel. And Hardev, if you don't mind checking the Slack channel and answering the questions there, that'd be fantastic. I'd like to introduce our next sponsor, which is Nikhil Prasad from Nutanix. Nikhil is a system engineer with a 17-year track record in the field of information technology, with a strong focus on multi-cloud and virtualization technologies. Nikhil has guided various organizations through their technological evolution by leveraging the Nutanix hybrid multi-cloud platform, resulting in successful digital initiatives, modernizing processes, and enhancing overall efficiency. So welcome to you, Nikhil, and thank you very much for being a sponsor, and floor is yours.
Thank you so much, Alan. Thanks, everybody, for taking the time. Today, I just want to briefly introduce you to the Nutanix cloud platform and sort of walk you through the value proposition and what the platform entails. So before we get into the technology bits, I just want to address what's sort of happening in the broader marketplace, right? The landscape has evolved. It has changed significantly, sort of making it challenging for the traditional businesses to operate in the way they have been. Everybody is looking to leverage the insights from all the different data points that customers generate using their mobile devices and are trying to evolve themselves into the digital business. Now, in order to keep up with the new business initiatives, IT also has to transform simultaneously, right? So in order to help businesses with the initiatives and help them stay relevant and deliver on new business outcomes, it requires IT to update their priorities and in turn is driving IT transformation as well. So when we talk to the teams that are typically tasked to adopt the new tools and capabilities and the new technology, their ask is typically very simple, right? So operators would like a common interaction plane so they can manage and operate their entire infrastructure while providing uptime versus managing different silos. They want the ability to automate different technology layers for operational excellence with security and availability built in. Engineers, on the other hand, require capabilities to deploy and scale infrastructure, be it up or down, based on applications that they support. This allows them to deliver self-service to end users and break down the barriers that hinder access to technologies. Developers, as they innovate against the business objectives, they need a working infrastructure. They just want something that they can consume using their own tooling and processes so that they can innovate, build, and deliver on new capabilities based on business asks, while working within the framework designed by infrastructure and engineering team. So for the IT leaders, the question often becomes where to start and how to deliver on all these asks. It is very complex because what they are dealing with on their end is possibly a very complex and siloed environment. And the reality is, in order to deliver on these new priorities, it requires a fundamental shift from how IT has traditionally been selecting, deploying, operating, consuming, and paying for technology. And the only thing that often comes to mind is, cloud as the savior for all these problems. But is it really solving a lot of the business problems, or is it simply creating another silo within the organization? And that's really where Nutanix can help as a platform. So by way of the platform itself, this was created back in 2009. It is a fully software-defined platform. Our founders came from Google, where they were building distributed file systems. So when we look at the Nutanix core platform, it's fully software-driven. We call it Acropolis operating system, or the Nutanix AOS, that serves as the foundation. What you can use for the underlying infrastructure are basically bare metal servers, right? So customers get the choice to pick the type of server that they want to build their platform with based on the workloads that they want to run. Through the platform, we also offer choice at that hardware layer. So regardless of any hardware agreements you have, you can essentially run the software on top with a hypervisor of your choice, be it ESX, Hyper-V, or you can even leverage our native hypervisor AHV, which is included with all of our solutions. Now together, these nodes form a cluster on which you can run your virtual machines, your applications, your workloads without any single point of failure. Your data is written twice or thrice, and it's distributed cluster-wide. Node and disk failures are handled automatically, where rebuilds happen in the background without impacting cluster operations. This architecture is essentially built to self-heal, and it uses spare capacity intelligently. We have identity access management, which is integrated, providing you the ability to report on different aspects of the infrastructure. It allows you to perform audits. It has the ability to tag your infrastructure resources based on the teams that are consuming it, and also build policies around them, be it from a data protection standpoint, security, or encryption perspective. Now, the idea is through the platform, the IT teams can now start providing services to achieve the business drivers set out. A few of the scenarios and the capabilities include database as a service, where the platform allows you to not only deploy, but patch, manage, and update databases through their entire lifecycle across a variety of different database engines. So whether you're using MS SQL or MySQL or Postgres, there's a multitude of database engines that are supported from an automation and deployment standpoint. From a storage perspective, the platform provides unified storage capabilities. So whether you need NFS SMB shares for your file services, your departmental shares, or you need S3 compatible object store for your backup repositories or for your analytical applications, or essentially block storage for your virtual machines, all of those services can be provided natively through the platform. And it's not just the creation of services that has been simplified, it's also the lifecycle management of these offerings that's also streamlined for IT teams. Now, the same freedom of choice applies if you choose to run Kubernetes or containers on the platform. We have the ability to support growing implementation of Kubernetes based on the model that's best suited, simplifying lifecycle management of Kubernetes. Now, when we start looking at AI and machine learning, and quite often we see developers create their own silos. They have their own code that they usually want to check in using GitOps framework and then execute that using a CI/CD pipeline in the public cloud. So essentially building the latest and greatest code, but they end up creating another silo for the organization to manage because they cannot deal with the on-prem infrastructure complexities. Nutanix solves that by plugins that are available via our APIs that allow that developer to consume the infrastructure and build their apps on the Nutanix platform without any change to the current workflow. And when we talk about providing users access, end user computing was one of that initial workload that our platform helped simplify. So we were able to offer consistent performance and scalability metrics for any organization to look at deploying VDI in a simple and meaningful way. This entire infrastructure running multiple applications, running multiple workloads is managed through a unified management plane that provides open APIs, command line interfaces, PowerShell scripts, and a very simple GUI to allow interaction with this powerful platform. Going back to the consumers of this platform, there's different ways you can interact with the platform, right? So I already touched on the GUI, the APIs that plug into your current tools. So when we look at operators and engineers, they can use this common interface to perform day-to-day tasks like hardware level upgrades, such as firmware and BIOS, or software upgrades of our core platform, the hypervisor, and the integrated services without any downtime. Operators can automate a lot of the day-to-day tasks with the capabilities built into the platform. So think of being able to right-size VMs, scale them up or down based on what the application requirements are, and being able to call out gaps to the business ahead of time so there are no delays in projects being implemented. Engineers can scale this infrastructure very easily by adding capacity to the platform without any interruption. You even have tools that help size and provide you the type of infrastructure that's required based on the workload requirements, removing the guesswork, allowing you to scale as your workloads evolve. Capacity planning and forecasting is built into the platform, so you're never in a situation where projects are put on hold. And finally, developers can easily integrate and consume this infrastructure like the public cloud. So if you're running Nutanix, you're essentially running your own private cloud. However, oftentimes we have customers who need to run in different locations, such as remote sites, for instance, a DR site, or a public cloud for that matter. Why? Because there's perhaps no interest in keeping an on-premise data center. And so a public cloud makes sense. Maybe you want to adapt a more granular pay-as-you-go model, or perhaps you want to choose a cloud-native service and you want your application to be close to that service, or simply have credits that you would like to consume. Whatever the use case might be, Nutanix can run on AWS and Azure and can be used as a tool to operate in the cloud without the need to modify and re-platform the application or change much of your operating model. In addition, we provide SaaS services as you scale across the multiple clouds that help you optimize costs, as well as make sure that you are secure as you go across the different cloud providers. So essentially, you should think of Nutanix as a strategic partner as you map out your cloud vision, because we help simplify, optimize, and accelerate adoption. Nutanix platform makes operations of all these applications uniform, regardless of where they live. So you get the benefits of that common operating model, elastic compute, security and automation built in, whether it's in your data center, in Azure, in AWS, or in a data center provider like Equinix, OVH Cloud, or Cyxtera. And this is the high-level architecture view. So regardless of what your workloads are, Nutanix as a platform provides choice at different layers, starting from the hardware, and provides different services to support business objectives. And that's really where Nutanix is as a company today.
Great. That's great. Excellent. Thank you so much, Nikhil. That was a great presentation. We're like the one before. For people that have questions, please put those into the Slack channel, right? Nikhil, if you'll go to the Slack channel and answer the questions there, that'd be fantastic. But thank you very
so much, Alan.
And we appreciate your sponsorship for the program. And with that, we'll wrap up this particular session. And I turn it back over to you, Taylor.